Now that we've established frameworks for analyzing both ideal solutions and ideal gas mixtures, what we're going to do now is we're going to look at the case where we have an ideal gas mixture in contact with an ideal solution. Consider a mixture in contact with an ideal solution. And so picture this, that we just have, vapor and liquid phases in contact with one another, where the liquid phase has 1 and 2 components, and the vapor phase has Y1 and Y2 mole fractions. Okay? And we could also consider the case, or consider the system in which species 1 is acetone and species 2 is methanol. Okay? And the reason I'm picking these two cases is that acetone is not that soluble in methanol. Okay? And so we would expect the mole fraction, the equilibrium mole fraction of acetone in the system to be much, much lower than 1. And so in that case, what we're going to be describing is a dilute system. Okay? And so for systems where x1 is very, very small, this is what is observed with regards to pressure. Okay. So if you could somehow measure the partial pressure of species 1 in the vapor phase, okay, this is what you would see. So let the x-axis be x1, y-axis be p1. You would expect to see a curve like this. Okay? Alright? And so what we're looking at here, what we're focusing on is the region where x1 is very close to 0. So it's much less than 1. And here, in this region, we find that the partial pressure of P1 is linear with x1. So linear at x1, much smaller than 1. Okay? Or another way we could say this, at least in words, is that the dissolved concentration of species 1 in the liquid, it's proportional to the partial pressure of species 1 in vapor. Okay? And so this sort of experimental observation or the experimental relationship, this is known as Henry's law. And so if you remember from MEB1, Henry's law basically says this. The partial pressure of some species that's very dilute in liquid, the partial pressure in the vapor phase is going to be equal to H1 times some X1. Okay, so let me label everything. Sparingly soluble, well, partial pressure of in vapor phase, okay, and and this is the Henry's law constant. So you could write it in terms of mole fractions, or you could write it in terms of just concentrations, so like a mole per liter. The only thing that would change it is the units of your Henry's law constant. And in general, as solubility of that component of the component 1 in the liquid goes down, you would see an increase in your Henry's law constant. Okay, so that's the general relationship that you would see. In any case, so the reason I wanted to introduce Henry's law here is because let's say we wanted to figure out out our concentration value. Okay? And let's say we knew what H1 is and we can measure what the partial pressure is. Okay, so how can we figure out what Xi is? To figure it out, what we could do is we could apply our equilibrium criteria and figure out X1 by equilibrium criteria. And our equilibrium criteria are going to be that the temperatures in the liquid and the vapor phases have to be equal. The pressures in the liquid and the vapor phases have to be equal. And also, the chemical potentials of a species I in the liquid phase has to be equal to the chemical potential of a species I in the vapor phase. All right, so be very careful about this one. It's not saying the chemical potentials of the two different species are equal. It's saying that the chemical potential of one species in the liquid phase is equal to the chemical potential of that same species in the vapor phase. Okay? All right. So, with these criteria in hand, what we could do is we could say that the chemical potential in the liquid phase is equal to the chemical potential of species 1 in the vapor phase. And since we're assuming that we have an ideal gas mixture in the vapor phase, we could write out the form of the chemical potential that we derived previously. T natural log of P1 over Pref. And then if I plug in Henry's law, I get this. And then, applying my log rules, I get split out the RT ln of Xi term. Okay? And the reason I write it like this is that these terms on the left-hand side here, these are independent of composition. And so our composition dependence we could isolate to just one term over here.